I'm Guilherme Vicinansa, and I'm going to talk about quantizer design for switched linear systems with minimal data rate. This is my joint work with Professor Daniel Librizon. So here's an overview of the talk. First, we introduce our problem and say why it is important. Then, we give some definitions and preliminary results. Next, we present our main contribution, that is the quantization algorithm that works with a data rate, average data rate as close to the minimal one. After that, we are going to present some simulation results, and finally, we talk about our future goals and ongoing work. So we're interested in the problem of control and estimation under communication constraints. So those problems arise whenever we have a controller or supervisor in one place and the system in another one, and those need to communicate through a communication channel. Now, communication channels impose constraints on the data rate that we can use in that communication. And those constraints impose limitations on what control or estimation tasks we can solve. For instance, it is known that there exists a minimal data rate below which you cannot stabilize an unstable LTI system. So that makes it clear that we need to deal with estimation and coding simultaneously. Therefore, some natural questions arise. So what is this minimal data rate for our estimation problem, and how can we build a quantization scheme that operates close to it, with a data rate close to it? So whenever we ask ourselves, what is a minimal data rate for a specific control or estimation task, the answer is normally related to an entropy notion. So the most widely used concept of entropy in dynamical systems is the concept of topological entropy. So topological entropy describes the rate at which a system generates uncertainty. By that, we mean how fast nearby trajectories spread apart from each other. So for several different control and estimation tasks, people have introduced distinct entropy notions. In this present talk, we are going to use the concept of estimation entropy, which is related to the problem of estimating the state with an exponentially decaying error bound. Also, we need to mention that some work on quantization and estimation have been done on the field of limited data rate. And here's a non-extensive list on those subjects. Here is a motivating example. So we consider this discrete time switched system where the matrix AN can either be equal to the mode B1 or the mode B2. And our goal is to build a quantization scheme that estimates the state xn with an error that decays exponentially fast. So we know that since the mode B2 is unstable, if we build a quantization scheme for each mode individually, we are using the conventional quantization schemes. We know that the data rate that we are going to need is positive, even when the exponential rate of decay of the error is equal to 0. So even in the case when our error is just constant, it's bounded by a constant. So, however, we are going to prove that if we know the switching signal, we can perform better than that. In fact, for this system, if we know that the switching signal comes from the realization of a Markov process defined by the Markov chain using this matrix of transition probabilities P, then we can reconstruct the state with an average data rate arbitrarily close to the estimation entropy. And for this specific case, when we consider that the error is just bounded and not exponentially decreasing, then the estimation entropy is actually equal to 0, and we still can operate arbitrarily close to that, which is already better than treating the modes individually. Now, what we understand by a switched system is a continuous time system with discrete events. Here we are going to slightly abuse the notation, and we call this matrix AN to be the state transition matrix between two consecutive sampling times. Also, the sampling times are going to be integer multiples of the sampling period, although we can relax that assumption. So we also define psi of xn to be the solution of the initial value problem when we start at state x and we flow it at time n. And we also denote by phi n this matrix product an to a1. Now we introduce the concept of estimation entropy. So given an exponential rate of decay, alpha, and a time horizon t, then for every epsilon greater than 0, we can call a finite set of functions x hat, where each one of those functions is defined from the time horizon 0 to t to rd, t epsilon alpha k approximating set if for every initial condition belonging to k, then there exists a function in x hat such that the error between the state is decreases by that exponential upper bound. Now, since x hat has a finite cardinality, we can define the minimal cardinality of all possible t epsilon alpha k approximating sets. Now, if we ask ourselves how fast this minimal cardinality grows with time, so if we increase the time horizon, we can ask ourselves how fast will that grow, and the estimation entropy is just the exponential rate of growth of that quantity, and it's given by this expression at the bottom of the slide. Now we switch gears a bit and we introduce the concept of Lyapunov exponent. So the Lyapunov exponent of sequence of matrices is a function that is defined by this quantity that depends on this limit superior on the right. It's also not hard to show that this function lambda attains at most d distinct values, and we denote those values by chi I. So here are some examples. So the first example is just a constant sequence equal to b1. And in this case, the Lyapunov exponents are equal to the logarithm of the eigenvalues of b1. Another example is given by this sequence here. So we have b1, and then we have 2 b2s, and then 4 b1s, and then 8 b2s, and so on and so forth. In this case, the Lyapunov exponents are greater than 0 independently of what v we choose. And the reason for that is because we used limit superiors in the definition. So essentially, given any v, you can show that the growth rate, there exists a subsequence of the sequence such that the growth rate is positive. Another related concept is that of Ozaldat's filtration. So a filtration is a family of vector subspaces that satisfy this ascending chain condition. And we call a filtration that is associated with the Lyapunov exponents in this way where EI is given by the vector such that the Lyapunov exponent is upper bounded by chi I. We call such filtration an Ozaldat's filtration. And now we also call lambda I the Lyapunov exponents with multiplicity, where the multiplicity is the difference between the dimension of ej plus 1 and ej. Another important concept is the concept of normal basis. So a normal basis is a basis for the space such that the restriction of it going from I to the dimension of ej is also a basis for ej. So here's an example. So if we consider a constant sequence then d of Zelda's filtration is going to be given by these three subspaces. In the first case, we have that E1 is simply the direction that grows the slowest. In fact, it doesn't grow since it is just equal to 1, since the eigenvalue of A in that position is just equal to 1. And then we have the subspace E2 that is composed by all the vectors such that their growth rate is upper bounded by log of 2. And E3 is the subspace of all vectors such that their growth rate is going to be smaller than log of 3. Notice that in this case, Lyapunov exponents are just the eigenvalues, the logarithm of the eigenvalues of this matrix. And also, the normal basis to this filtration is just composed by the eigenvectors. Now, we build a bridge between the concept of estimation entropy and Lyapunov exponents. To do that, we need to define this concept of regularity. So given a sequence of matrices, we call this sequence regular if we have this compatibility between the determinant and the Lyapunov exponents. On the right-hand side, we have a quantity that depends on the growth rate of the state, and on the left-hand side, we have a quantity that depends on the growth rate of the volume. Just remember that the determinant of the flow is related to the growth rate of the volume. So here is an example of a regular sequence. So if we start at mode B1 and then we go to mode B2 and then we keep switching periodically between those two, we realize that the determinant of phi n is equal to 1 for every n. So the limit on the left-hand side is equal to 0. And also, it's not difficult to see that the Lyapunov exponents in this case are both equal to 0, since we have that phi n is either equal to the identity or equal to B1 for every n. So the state is not growing. So the Lyapunov exponents are both equal to 0. Now, if we go back to that example where we had B1 and then B2 twice and so on and so forth, we have that the lambda v's are greater than 0. However, the left-hand side is always equal to 0 because phi n is equal to 1. The determinant of phi n is always equal to 1. So the left-hand side is equal to 0 and the right-hand side is positive. So the sequence cannot be regular. Now, we can use that information to prove a connection between the estimation entropy and the Lyapunov exponents. And that's given by this equation here. And also, even when the system is not regular, we still have this upper bound. And to give you an idea of why is that true, essentially, whenever we prove an expression for the entropy, we normally prove an upper bound that's related to the growth rate of the state and a lower bound that is related to a volume growth argument. And using those two quantities and the fact that the system is regular, that gives us a compatibility between those two concepts, then we can prove this equality. But in general, we don't have that compatibility, and we can only have the upper bound. Now we have all the pieces so that we can discuss our main result. So here are some of the algorithm parameters. So we have L, that is this so-called block length. This is how many sampling times we need to wait between two quantizations. So Vj is a family of orthonormal bases for Rd. Notice that this family is rather arbitrary, other than being orthonormal. Also, we introduce this quantity that is gamma ij, that is related to how fine our quantization is. And it can either be given by the first expression when we know that the system is regular, or it can be given by the second expression when the system is not known to be regular. And the second expression has this extra term that is this delta, that is an arbitrary constant that's related, that is actually going to penalize or is going to increase the data rate that we use in our quantization scheme. And finally, we have Cj, that is the set of quantization symbols. So first, at iteration j plus 1, we have that the state belongs to this box b bar j with sides that are parallel to vij. Then we construct a new box that contains b bar j and with sides that are parallel to vij plus 1, and we call it b theta j plus 1. Next, we flow that box and we get a parallel pipette called bj plus 1. And notice that since the initial state belongs to b theta j plus 1, then the state at time jl plus 1 belongs to this new parallel pipette. Next, we subdivide this parallel pipette into subregions, and we assign to each one of those subregions a quantization symbol. And to the region that contains the true value of the state, then we take that quantization symbol that corresponds to that region, and we call that the quantized value at that time. And also notice that our state estimate is given by the midpoint of the quantization scheme, the quantization region where the state is at. Following that, we take this quantization subregion and flow it backwards in time to get a new box b bar j plus 1. And finally, we repeat the procedure. Now, using that algorithm, we can prove theorem 5.1, that proves the correctness of our algorithm. Essentially, it proves that the estimation error is upper bounded by that quantity that decreases exponentially fast. And also, it gives us an upper bound on the cardinality of the set of quantization symbols, and that quantity is related to the data rate. So that will actually give us upper bounds to the average data rate utilized in this algorithm. So here's the idea of the proof. So looking at this picture, we realize that if we rewrite the state in the set of coordinates phi jl plus 1 times vij plus 1, we get the coordinates beta ij plus 1. We can do the same for x hat and get bij plus 1 hat. And we get that the error between those two betas is upper bounded by that quantity. Now, using that inequality and essentially applying the triangle inequality, we can prove that the estimation error is going to be upper bounded by that exponentially decreasing bound. Another fact is if you simply ignore the realignments, it should be somewhat natural to expect that the data rate to be essentially the division between the side of the larger parallel pipette in those subregions, and the side of that larger parallel pipette is essentially the error in the previous quantization step and this next subregion. So we're going to get this inequality here for the cardinality that relates to the ratio of gamma ij plus 1 and gamma ij. Now we ask ourselves, how do we choose the family of bases such that we can get the smallest data rate possible? And the answer is we choose a normal basis to the Alzada's filtration. The reason for why that works is because that ratio between gamma ij plus 1 and gamma ij for j sufficiently large is going to be close to e to the tp lambda il. And that's why we get this upper bound on the right hand side. And when we don't know if the system is regular, we need a bit more work, and we get the second bound that we get here on the fourth line. And we refer to the paper for the details on this. Now, we should be done. However, we are kind of cheating right now, since in order to calculate those bounds, in order to find those bases, we need to know the Ozaldat's filtration and the Lyapunov exponents. And knowing those require us to know the entire sequence AN beforehand. So another question that arises is, can we choose a family Vj so that it only uses information that is available to us up to the current time and still get an average data rate that is arbitrarily close to the minimum? And the answer is again yes. So consider this sequence of matrices Qj that is a family of symmetric positive definite matrices. And because of that, those matrices can be diagonalized by orthonormal bases. And we simply define Vj to be those orthonormal bases. And also, since those matrices are positive definite, we can define its eigenvalues to be the exponential of rho ij's. And we order the elements in that orthonormal basis using the order on the eigenvalues of Qj. Then we get those two possible upper bounds. Notice that both of them decrease when the block length increases. And also, we have this difference when we know the Lyapunov exponents are simple or not. By simple, we mean that the multiplicity of those Lyapunov exponents is equal to 1. And the reason why we get a worse upper bound when we don't have that Lyapunov exponents are simple is because of those alignments that we need to make between the bases in the previous step and the current step. Now, it can be shown that realizations of Markov jump linear systems are regular with probability 1. Therefore, we can use the expression that we have for the estimation entropy in terms of the Lyapunov exponents to find what the minimal data rate would be for our motivating example. So here we get this expression. Using the parameters alpha equal to 0.05 and epsilon equal to 0.01, we compute that the estimation entropy is approximately equal to 0.137 bits per sample. And in the next simulations, we are going to use the block lengths equal to 1, 3, and 5. So here in this picture, we see a purple curve that corresponds to the upper bound to the estimation error. And the other curves are the state estimates. As we can see, the state estimates satisfy the upper bound as we would expect. Now, in this picture, we see that the empirical average data rate, and we see that it indeed decreases. The average data rate needed decreases with the block length. However, all of these values are far from those upper bounds that we derived. And the reason is the average data rate is an asymptotic quantity. So it might take a long time until those values are actually inside those bounds. But it's still, notice that we can mitigate that effect by increasing the block length. So right now we are working on designing quantization methods that operate at data rates that are close to the estimation entropy for exponentially stabilizing linear switched systems. And in the future, we hope to extend these methods to nonlinear systems. So thank you for your attention, and here are some of the references used in this talk.